This is an A-level mechanics question on static rigid bodies. A plank AB of mass m and length 2a rests with its end A against a rough vertical wall. The plank is held in a horizontal position by a rope. One end of the rope is attached to the plank at B and the other end is attached to the wall at point C, which is vertically above A. A small block of mass 3m is placed on the plank at point P where AP is equal to x. The plank is in equilibrium in a vertical plane which is perpendicular to the wall. The angle between the rope and the plank is alpha, where tan alpha is 3/4, as shown in figure 3. Figure 3 is here. The plank is modelled as a uniform rod. The block is modelled as a particle and the rope is modelled as a light inextensible string. So here's our plank here, AB, with a small block on it here in grey, little block there, and the mass of the block is 3m. One end of this plank is next to a wall, a rough wall, which is vertical. And to stop the other end of the plank from just dropping down, we have this rope which is attached at B, and the other end of the rope is attached at C, and that is vertically above A, and we're given the tan of this angle here as 3/4. Okay, so the first thing I'm going to do is to take this tan alpha equal to 3/4 and use that to work out the exact value of sine alpha and cos alpha. So I'm just going to draw a right angle triangle here, call this angle alpha, and tan alpha is 3/4, so the opposite is 3, the adjacent is 4. Using Pythagoras, the hypotenuse is 5. So that gives me that the exact value of sine alpha is the opposite over the hypotenuse, 3/5, and the exact value of cos alpha is the adjacent over the hypotenuse, 4/5. So I will highlight that because I'm going to be using this later on. So what we don't do is try and work out the angle alpha, because we're going to get into all sorts of messy angles and non-exact values here. Next thing I'm going to do is to put my forces onto the diagram here. Let's start with the plank, which we're told is modelled as a uniform rod, which means then I can put its weight in the centre of that rod or that plank, and its mass is m. So that means in the very centre I will put a mass here, or a weight of mg. Now, because that's in the centre of the rod, we have a distance of a from the end of the plank. We've also got the mass of the small block, so its mass is 3m. So that means I'm going to put a weight here of 3 mg. Then where the plank is in contact with the rough wall, there's going to be a normal reaction, which we'll label R. The wall is rough, so that means that there is going to be a frictional force at this point as well. Now the plank wants to move down, so there'll be a frictional force going up, and for now I'll just call that F. Then the other force that we have is going to be the tension that is in this rope here, which I'll label as T. Now to complete part A, what I need to do is to take moments about point A. Now the advantage of doing that is that I will get an equation that does not include my normal reaction or the frictional force, because they're unknowns, and it will just give me the forces mg, 3mg, and the tension. So let's work our way around the diagram. So I've got a moment here at a distance of a and a force of mg. Remember that we want these perpendicular angles between the distance and the force, and I'll draw it as like a little diagram. So I've got a distance of a and I've got mg, so I've got A here, mg here, and that moment, so this is the point A, a little dot, this moment is one that's going in a clockwise direction. Then my second moment is going to be a distance of x to the free mg, so we'll just draw that. So distance of x going to my 3mg, so I'll put those on, x 3mg here. So these must be perpendicular, and this is also going to be a clockwise moment, like this. And then from point A, if I go all the way to the end here, I want to know what is the perpendicular component here for t. Now, this component here will actually be the same as this one here. Okay, it's just like in a different position, but it's the same size force, and I know that this will be t sine alpha, which means that this is t sine alpha. So we'll get rid of this bit here, and we'll just write over here t sine alpha, and there we have our right angle. So if I draw a diagram for this moment, this will be a distance of 2a going to this t sine alpha. So let's put that on, 2a and t sine alpha, and a little right angle in here. Now, because the plank is in equilibrium, we're told that here, what we know is that the sum of the clockwise moments is going to be equal to the anti-clockwise moment. So now we can write our moments equation, which is going to be mga plus 3mgx is equal to 2a times by t sine alpha. Now remember, up here we said that sine alpha is 3/5, so I can change this sine alpha to 3/5. So let's take that out and write times by 3/5. And from here I want to make t the subject, so let's flip the equation around. So if we multiply what we have here, we'll have 6a over 5t. So 6a over 5t is equal to, and when I put these together, I'm going to factorize it as well, take the mg out. So I'll have mg, and then in brackets a plus 3x. And then from here, I'm going to times both sides by 5. So 5 or t is equal to 5mga plus 3x, and then also divide both sides by 6a. So we get this is our tension. Now this looks pretty much the same as this, but whenever you get these proving questions, always write it in exactly the same form is given as in the question. So I'll write down, therefore, the tension in the rope is 5mg 3x plus a over 6a as required. Okay, the magnitude of the horizontal component of the force exerted on the plank at A by the wall is 2mg. Now that is this force here. This is the horizontal component of the force exerted on the plank at A, and we've been told that that is 2mg. So let's write that down. And in part B, it says that we need to find x in terms of A. Now to find x in terms of A, x is horizontal, and this distance A is horizontal. So that means that I'm going to be resolving forces horizontally. So I have this horizontal force here, 2mg. I also need to find the horizontal component of the tension. So let's draw that in. That will be going in this direction, and that will be t cos alpha. So my equation is going to be 2mg is equal to t cos alpha. You'll remember from part A, we wrote down that cos alpha is 4/5. So I'll have 2 mg is equal to t times by 4/5. And also from part A, we've got the exact value for t. So we're going to substitute that in as well. So we'll have 2 mg is equal to 5 mg times by 3x plus a all over 6a, that's my t, times by 4/5. So before we go any further, let's see if there's any cancelling down I can do. Yes, I can cancel down the 5. The 6 and the 4, I can divide both of those by 2 to give me 2 here and 3 here. Which also means I can now divide both sides by 2. Cross that out and divide both sides by mg. So a lot of cancelling down. Now on the left hand side that will leave me with 1, not 0. And then on this side here I'll just be left with 3x plus a over 3a. Multiplying both sides by 3a, I will get 3a is equal to 3x plus a, which means that 2a is equal to 3x. So x in terms of a will be 2/3 a. So let's highlight that, and we'll probably write it down at the side as well, because this will probably be useful for the next part of the question. The force exerted on the plank at A by the wall acts in a direction which makes an angle beta with the horizontal. Part C, find the value of tan beta. So let's draw a diagram to see what it looks like. So we're talking about the angle that the combined lot of these two forces make. So let me draw a diagram of that. So I've got this frictional force acting up. I have my 2 mg acting horizontally, and then the total of that force, which we'll have acting in this direction here, is an angle of beta with the horizontal, and I need to find the tan of this angle. Now to find this angle I need to know what these two components are. Well, I know this one is 2 mg. What I don't have yet is this force here, and the only thing I haven't done in this question yet is to resolve in a vertical direction. So let's look at what the horizontal forces are. Well, we have F and T sine alpha going up, so F plus T sine alpha is going to equal the downward forces, and so that's going to be mg plus 3 mg. We want F, so F is going to be equal to, well, if I've got mg plus 3 mg, that's 4 mg, then minus T sine alpha. So let's substitute what we have for T and sine alpha. So T is the same T that we had from before, so that's 5 mg 3x plus a over 6a times by sine alpha, which is 3/5. So we'll cancel down again, so the 5s are going to go divide the 6 and the 3 by 3, just leaving a 1 here and 2 here. And then we can also substitute the x here for 2/3 a. That's what we worked out in the previous part. So this x here, I'll put 2/3 a in there. So that'll give me F is equal to 4 mg, and then minus, now I'll have mg, and then 3 times by 2/3 a plus a all over 2a. Now the a's will cancel out, because if I were to expand the brackets, every term would have a in it. So it simplifies even further. So I've got F is equal to 4 mg minus, and then this will become 3 times by 2/3, which is just 2, plus 1. Remember this, that will cancel down to 1. So all of the bracket here will become 3, and I'll have 3 over 2. So I can put minus 3 over 2 mg. So from there, F is going to equal to, I think, 5 over 2 mg, 4 minus 1.5, basically 2.5, yep. So on my diagram here, this F I can write as 5 over 2 mg. So let's take that F out and put 5 over 2 mg. That is going to be the same as this length here over the other side. So the tan of that angle beta, so tan of the angle beta is going to be the opposite over the adjacent. So that will be 5 over 2 mg over 2 mg. The mg's cancel out, lots of cancelling out in this question. And now that just leaves 5 over 2 divided by 2 is 5 over 4. So tan beta is equal to 5 over 4. Okay, last part. The rope will break if the tension in it exceeds 5 mg. Part D, explain how this will restrict the possible positions of P. You must justify your answer carefully. Okay, so we want basically the tension to be less than 5 mg. If it exceeds that, actually we could say that the tension needs to be less than, it could be equal to 5 mg. But if it exceeds that, then it's going to break. So we want tension to be less than that. So we can take our expression for the tension and put that for T. So we've got 5 mg 3x plus A over 6A needs to be less than or equal to 5 mg. Now we can divide both sides by 5 mg. So that will give us 3x plus A over 6A is less than or equal to 1, not 0. We'll times both sides by 6A, so 3x plus A less than or equal to 6A. And then we can subtract A from both sides, so I'll have 3x is less than or equal to 5A. And then divide both sides by 3, so x is less than or equal to 5 over 3a. So I'll put my conclusion in words. For the rope not to break, P needs to be no more than a distance of 5 over 3a from A.